Good morning, and welcome to your second of many calculus whiteboard screencasts. It's always a little funny to say good morning because you may not be watching this in the morning. In fact, you probably aren't. But just for the record, it's 3:46 a.m. and I wanted to get this up for you guys just in case some of you are ambitious and want to watch it right after class. So now's my chance, and I got to do some editing and some other stuff. So hopefully we can get this done. But if I make some stupid mistakes or I sound a little silly, please bear with me. Note 3:46 a.m. All right. So yesterday we talked about, or in the last lecture we talked about finding secants and slopes, and we could find that a secant line kind of becomes a tangent line when this h becomes really small. Well, what we're really doing is taking the limit of this slope when h goes to 0. So we're going to investigate that in a little bit more detail right now. But as usual, I try to start off with something not calculus related, and because I don't want to scare you away with math stuff right away. So I'm going to ask myself, what is a limit? As it pertains to you ready for it? Pony Express. Now, what the heck am I talking about? This is the description I've used for many years, and it works pretty well, so I'm now going to throw it out there for the whole world to hear. But for those who don't know the Pony Express, it was a means before airplanes and cars and high-speed travel, email, texting, Instagram, Twitter. Say if we're going to go to war with the British again and we have to get a message, let's draw a quick little. Now this is getting silly. So here we've got some Great Lakes and some kind of funny border here, and then we have Maine, and then we have some coast like this, and then Florida, and then I don't know, Texas looks something like that. I go like this. Say we need to get a message from Washington D.C. or actually Annapolis at the time, and we need to get a message, all the way out to the, here somewhere, the territories, that we're going to war with the English again. Well, what we do back in the day is, have give the letter to some guy on a pony, and he would ride really fast, and then his pony would get tired, so he'd hand it to another guy, and he'd run really fast on the pony, and then that pony would get tired, and he'd run really fast. And of course this would take days or weeks, but it's the fastest way to get a message from one place to another, riding from pony to pony. Well, years later, and barbed wire was invented. All right, now why does barbed wire have to do anything with the Pony Express, and why does the Pony Express have to do anything with limits? Well, here we go. Let's say that one particular stretch of the Pony Express, green for a trail, kind of went along like this. Da, 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 da. Kind of here's this trail, went like this. And then someone came along, some rancher, and said, well, he wants to keep his cattle kind of close by, so he gets a barbed wire, which sometimes is reddish looking. And so he puts this barbed wire fence here. Okay, so this is a fence, and this is a trail, like that, right? Well, now we've completely destroyed the Pony Express, right? There's no way this system will work anymore. Well, actually, I think it will, because we can have one pony ride along here. So let's say pony 1, rides along here and stops, and then pony 2 can pick it up. They just hand it across the fence, and pony 2 continues its way over like this. Right? So really, this barbed wire fence here, as long as pony 1 and pony 2, well, I don't know if it's the ponies or the riders, I'm not much of a horseman, but as long as they meet at the same spot at the fence, they can just hand it over, and the message can be delivered just fine. All right, so let's call this case number 1. All right. Case number 2 would look like this. Say we're trying to establish a new, a new pony route that heads down here to Arizona or New Mexico, but there's already a fence in place. So this was a new fence, and this is a old fence. And we're going to call this case number 2 here. Case number 2. So now we've got some other deal. We've got another trail that's coming along here. That we're forging this trail. The pony runs along this way, but it comes to a fence. We can walk right up to the fence, very close, but there's not going to be this well-worn trail going underneath the fence line like there was up here. There's just going to be kind of some nice grass growing. It's going to look like nothing ever happened there. And then, on the other side, we can have some, trail going like this. So do you see there's a subtle difference here? Here I lost my cursor again. So here the trail goes right under the fence, but we just have to make the handoff here. Here there is no trail. The trail doesn't go under the fence, but it's still not a problem because we're going to hand it off across the fence like this. All right, so this is same deal. Pony 1 rides that far, and then Pony 2 can pick it up where Pony 1 had to stop. All right, so it's all good. Now let's look at case number 3. And here we'll say we have a fence again. Like this. And then we've got the first pony rider is cruising along here. And he stops right there. And of course he can't actually go under the fence, so we'll draw a little open circle there. And then Pony 2 is coming along. So this is Pony 1. And Pony 2 comes along, he's cruising along like this, and then stops right here. And say maybe this guy even sits on the fence as he's waiting. So you can actually sit right there on the fence. Well, this isn't going to work so hot because Pony 1 and Pony 2 don't meet at the same spot on the fence. So they're not going to be able to send the letter, hand the little letter or the message across the fence, indicating that we're going to war with England again. And I don't know, the New Mexico people just kind of live happily ever after without knowing they were going to war. All right, so now that this has gone long enough, case 1, there's a fence here and we just hand the letter across. Phase 2, there's an old fence, but the trail can go right up to the fence and then start on the other side. Case 3, the two places don't meet. What am I talking about? I'm talking about limits. And we say the limit as x approaches some value, let's just call it a, of f of x. Right, so a really is our fence, so we'll label that as our fence, and the trail is really our green thing here. And so this is the question that we're asking here. I always like to think of this math stuff as a question, is what y value does f of x get close to? I know that's not the best grammar. As x gets close to a. All right, that's what we're asking. So x is going to get really close to a, or the pony is going to get really close to the fence. What is the y value? Where are we going to end up? Here they ended up in the same place, no problem. Here we couldn't actually cross the fence, but we both were at the same place at the fence. Here we wound up at two different places. All right. So, I think this is best described now with some examples, and hopefully we can relate these back to this crazy idea of the Pony Express. So what if I said, find the limit as x approaches 1 of the function x plus 1 equals, right? What is that going to equal? Now this may seem really obvious, but if we maybe draw a sketch of this, draw that like that, and let's see, the intercept is going to be 1, so it goes through there, and it's going to have a slope of 1, so it goes up like that, and when x gets really close to 1, well, that's just going to get really close to 2, right? So this equals 2. Now, that was kind of dumb. We could have just plugged the 1 into here. So 1 plus 1 equals 2. No problem, right? Okay, what if we took a little more difficult one? And I said find the limit as x approaches 1. So again, my x value is getting very close to 1. My function in this case is x squared minus 1 all over x minus 1. All right, we learned in the last example that maybe the easiest thing to do is just to plug a 1 in here, right? X is going to get close to 1, so we have, let's see, 1 squared, which is 1 minus 1, over 1 minus 1, which equals 0 over 0. 0 over 0. That's not good. Let's put that in red now. This is not barbed. Well, yeah, barbed wire is also not good. Not good. Why is that not good? Because we can't divide by 0. Division by 0 is bad. Alright, so we can't just plug it in. So we're going to use some algebra. What kind of algebra are we going to apply? Well, we've learned how to factor. That's kind of old news. So we can say the limit as x approaches 1 of, let's see, x squared, that factors out to x plus 1, x minus 1, all over x minus 1. Ooh, and this is pretty cool, because we can now cancel out these x minus 1s. Right, so now that equals limit as x approaches 1 of just x plus 1. So it's the same as it was before. But we can't just do that. Right, we have to say x not equal to 1, because when x equals 1, we've got a problem down here. That gives us division by 0. It's going to look like the limit of x plus 1. So what this thing is really going to look like is this. Let's see, we'll do it over here. We'll say x squared minus 1 over x minus 1 looks like, we'll just make a little sketch of this here. Here's 1. There's 1. And it's going to look just like x minus 1, x plus 1, except that we're going to have what we called a point discontinuity at x equals 1. So we've got this little division problem when we go down to here. We know, that this value is going to be 2. We know that. But we can't say that x equals 1, just like we can't say h equals 0. But as we get really close to 1 in this direction, the value of the function is going to get really close to 2. So that's using some algebra to get at a solution that we otherwise couldn't find. All right, let's look at another example. Go back to my black pen here. Find the, let's say, limit of f of x as x approaches, let's just say 1. But I'm going to define f of x over here equals, I'm going to make it a piecewise function. I'm going to say that it's x plus 1 if x is greater than, or if x is less than 1, and it's going to just equal 3 if x is greater than or equal to 1. All right, so what's that going to look like? Well, let's make a sketch. It's always good to make a sketch of these things. And well, x plus 1, we've drawn that a bunch of times, but the rule says as long as x plus 1 is, if x is less than 1, the function will be x plus 1. So we'll say here's 1, and we'll have to make a little fence there just because that's kind of where the rule changes. And here's our intercept. The slope is just 1, so this thing looks like this. But we have a little hole there because we're not allowed to go right up to 1. We're only allowed to get really close. It's got to be less than 1. And then and we know this is 2. And it's 3 if x is greater than or equal to 1. So we go all up here to 3. And so greater than or equal to means it's a solid circle. And it goes off like this. So what is the limit of f of x as x approaches 1? Well, coming from the left side here, it appears to be, we're going to get really close to 2. Coming from the right side, it appears to be equal to 3. So that's a problem. So this limit does not exist. In math, we'll see this a lot. Does not exist. Okay. We'll talk more about approaching from the left and approaching from the right and how those give us different answers sometimes. That'll become important. All right. Next up, some basic limit rules. I don't like the word rules, but I'm tired and I can't come up with a better one for now. So we're going to insert a picture here. And that picture will be limit rules. So we'll just slide this guy up here, make it a little bigger so you guys can read it. I don't want to make it, there we go. Let's get it tipped there. Now it's crooked. How does that look? Pretty straight? All right. So here's some properties of some limits. First of all, if the limit of, we have some function f, and x is going to approach c, right, equals L, whatever, right? This is generic mathy kind of term, so it takes a long time to read this mathy kind of language. So let's think about it. We have some function, and x is going to get really close to our fence, whatever that is. We're going to call it some generic c, and we're going to call that limit L. Why L? Because L stands for limit. And we've got another deal here, another function, g of x. X is approaching the same fence. This limit equals k. Why doesn't it equal L? Because we already used L. All right, so we have two functions, two trails, the same fence, and they're going to hit the fence at different spots, L and k. Scalar multiple rule. If we multiply the function by 5, well, the limit is just going to be 5 times what it was before. Sum or difference. If we add the two functions together, the limit will just be the sum of the two things. product, if we multiply the two functions together, well, the limits will just get multiplied together. Quotient, power, these all work the same thing here. Now, these may seem silly. They may seem, let's call it, these are vague and a little obvious even, of course. Right? Well, let's look at an example. Let's say that f of x equals, I don't know, so let's pick something easy. How about x? Right? And let's say that g of x equals 1 over x. Okay. Well, if I look at these limits individually, I can say the limit as x approaches, let's say 0, of x equals, well, we'll plug a 0 in there, it'll be 0. Right? We could say the limit as x approaches 0 of 1 over x. Now, what does 1 over x look like? Let's maybe make a quick sketch of that. Well, 1 over x, when x gets small, it gets really big. It looks huge like that. That goes out like that, and this one comes down like that. So as I approach my fence, as I approach 0, there is no limit. It never even hits the fence. So this thing doesn't exist. Right? Whereas if I said the limit as x approaches 0 of x times 1 over x, right, which is really f times g, this would equal, well, x times 1 over x is just 1. And we know the limit as x approaches 0 of 1, well, that's always just going to be 1. Right, but we can't do this. Right, these are different because the limit doesn't exist independently for f and g. So we can't say that works out that way. All right, so let's cross that out just so we know that this is dangerous. We can't do that. Now this will surely confuse you, and I expect it to confuse you. These limits are weird. It's your first real exposure to limits, so it's a little confusing. That's okay. Please ask me about it in class. All right. Now, in fact, I'm going to make a little note here. The limits must exist on their own before we can apply limit rules to combine them. All right, okay, so that's very important. All right, last, let's do some examples. Let's go back to the black pen here. Example. All right. I'll do another one, algebra. Okay. We've done one where we did some factoring, canceling out. Actually, this isn't algebra. This is going to be simple. I'll even say simple plug and chug. So the limit as x approaches, I don't know, how about 4 of something pretty straightforward, x squared plus 3x minus 7. All right. Well, I'm an engineer, right? Engineers kind of by nature, we're always looking for problems. We're looking for what issues do I have? What problems are there? How could this thing break down? Well, I don't have any division by 0 like we had before. I don't have any square roots with negatives or anything like that. So I can just plug and chug. Let's see, 4 squared, well, let's just do 16 minus 12 minus 16 plus 12 minus 7 equals 28 minus 7 is 21. Okay, so I can write the limit as x approaches 4 of x squared plus 3x minus 7 equals 21. Put a box around that because that's my final answer. Like that. Okay, fine. Now let's do one where we have to do some a little bit of algebra. Okay. How about the limit as x approaches 1? Why do I use 1 all the time? Because it's easy. I don't want to spend time doing arithmetic and multiplying and squaring big numbers. I just want to understand the mathematics. It's going to be 1 over x minus 1 all over x minus 1. All right, well, yeah, I'll be optimistic here. Let's just say we can plug and chug, so that's 1 over 1 is 1, minus 1 over 1 minus 1 equals 0 divided by 0. Once again, division by 0. And we call this 0 divided by 0, we call this indeterminate. All right, well, what kind of algebra can we do here? Well, I see, whoops, what happened there? I see two fractions here, so maybe I can make a common denominator. Well, I need, on the top, my common denominator would be x, so that's 1 over x minus x over x over x minus 1, and that would equal 1 over x minus x over x is 1 minus x over x over, now I'm going to have a kind of this compound fraction here. I'm just going to make this x minus 1 over 1. What do we do here? We flip that guy and multiply. So it's 1 minus x over x times x minus 1, or 1 over x minus 1. And hopefully you guys are, that 1 minus x and x minus 1, those are opposites. So this just equals negative 1 over x. Right, now I can plug in x equals 1. And that gives me, let's see, negative 1 over 1 is negative 1. That's my final answer there. Okay, so here, what did I do? I had to do some algebra. I found a common denominator, subtracted, combined some things, flipped it, simplified, and I got a negative 1. All right. If I didn't simplify first, I would have 0 over 0 still, which leaves me, no better off than I was before. All right, another technique. And this is called rationalization. Wow, what a word. Rationalization. Let's take a look. I want to do the limit as x approaches. Should we mix it up? No, we're not going to mix it up. As x approaches 1 of x minus 1 over root x plus 3 minus 2 equals, well, we can be optimistic again, plug the 1 in. 1 minus 1 is, x, 1 minus 1, we can see where this is going. X plus 3 is 4, square root of 4 is 2, 2 minus 2 is 0. Foiled again. Alright, so we've got to do some algebra. What am I going to do? I'm going to multiply by the irrational conjugate, or the radical conjugate, which will be root x plus 3 plus 2. So I'm going to say x minus 1 over root x plus 3 minus 2. And I'm going to multiply this thing by root x plus 3 plus 2 over root x plus 3 plus 2. Okay, what does that give me? I wonder if I can fit this in here. If I foil, if I foil this thing out, x times root x plus 3 is x times root x plus 3. X times 2 is plus 2x. Minus 1 times x plus 3 plus 2. Let's see, minus, right, outside, inside, minus root x plus 3. And then, let's see, minus 2. Right. All over. When I foil this becomes the difference of two squares. So it's root x plus 3 times root x plus 3, which is just x plus 3. And then minus 4, right? No. Yeah, minus 2 times plus 2 is minus 4. So we can simplify this again. I'm going to collect my terms here. So it becomes an x minus 1 times root x plus 3. And then what I have left here, plus 2x and minus 2. All over x plus 3 minus 4 is just x minus 1. Now, look at this. I've got an x minus 1 here. What am I going to? I'm going to 1. So a 1 actually gives me a problem because x minus 1 gives me 0, so that's division by 0. But I'd like to cancel that out somehow. So look what I can do here. I'm going to say it's x minus 1 times root x plus 3 plus 2 times x minus 1 all over x minus 1. Now isn't that nice, because I can get out the all-powerful red pen of cancellation. Now I've got an x minus 1 in everything. So I can cancel, cancel, cancel. That's pretty nice. So now, lost my pen, equals, cancel, 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 so that's just simply root x plus 3 plus 2. And I plug in x equals 1, and that gives me 1, 2, 4. Okay, there we used a radical to rationalize our our expression here, and then our problem ends up canceling out. And that happens a lot. Finally, there's one more thing I'd like to talk about. Actually, two things, but one leads to the other. And that is some books called the sandwich, and it really is called this. This isn't something I'm making up. The sandwich, squeeze, or pinch theorem. Well, whatever. And what that says, if I have, let's see the notation, I like to use if I have some f of x, right, and I'm trying to find that. And f of x is always smaller than or equal to some bigger function, b of x. And it's always bigger than a smaller function, s of x. Right, so if we have this, so if f of x is between a small function and a bigger function, it's squeezed or pinched or sandwiched between those two, always. And limit of, as x approaches a, of s of x, the smaller function, is the same as the limit as x approaches a of the bigger function. Right? What does that mean? Well, let's just sketch a picture here. I'll do this in multicolored because it's late and colors are fun. So if I have, you know, if I do the big function, which I do a big one in, how about orange? Because I like orange. If the bigger function, say, goes like this, you know, it goes like that maybe, and this is b of x, and my smaller function, blue, because a robin's egg is small, and so the little function kind of does this. That's the smaller function. Now, if my function in question, and say this is a, if my f is in here somewhere, it doesn't matter what it does. If it's always between these two, it's got to sneak through there. So that means the limit as x approaches a of f of x equals, let's call this L, also equals L. All right. Now that's a little odd. This is a very tricky tool to use. But as things usually go in math, but very powerful. All right. I'm going to use a somewhat easier example. Say, find the limit as x goes to 0 of this funny looking one, x squared times cosine of 30x. Now this 30 is just kind of, I'm going to make a note here, blue. The 30 is kind of arbitrary. Right, what does that do? The 30 really speeds up the cosine function. So instead of going a nice, up and down, up and down, it's going to go up and down, up and down, up and down, up and down, up and down really fast. Right, that'll just help illustrate our point. Up and down between what? The biggest it gets is 1, and the smallest it gets is -1. And this x squared is a parabola. Right, so this function is going to look a little bit like a parabola. The biggest it'll ever get is it'll look like x squared, and the smallest it'll ever get is -x squared. Right, so this thing is always kind of pinned between x squared and -x squared. So if I could write this, x squared cosine of 30x, well, the biggest this will ever be is 1, so this will always be at or below 1 times x squared. And the smallest it could ever get is -1, so it'll always be bigger than -x squared. All right, so x squared cos 30x is smaller than x squared, and it's bigger than this. So I know that x squared is going to get close, -x squared, limit as x approaches 0 of negative x squared, well, that equals 0. The limit as x approaches 0 of positive x squared, well, that also equals 0. So this thing has got to be in between. All right, let's take a look at that. I used a little program called Algebra here, which is a really slick little program to plot these things. So here's my function, x squared cosine of 30x. What does that look like? Yeah, it just kind of goes, oscillates wildly back and forth. The biggest it ever looks like is x squared. The smallest it ever gets is negative x squared. So if we plot the upper bound, right, it's always above that. Or it's always, so our function in question is always squeezed in between these two. And then at the center here, they both go to 0. Right, so that becomes a picture of what we just tried to prove. Now, I didn't think I had to put this in the notes, but I'll do that before I post the notes. Okay, I hope you find that useful. I'm sure there'll be questions. This is hard stuff. It's tricky stuff. It's your first exposure to limits. So bear with me. Ask questions in class. Try the worksheets. We'll figure this stuff out.